Let's begin as we always do by connecting to your bank. When you want to connect to your bank, you would like that connection to be secure. So part of that means you need to send information like your username and your password over the internet. Basically, you need to have a way to establish secure communications over an otherwise insecure channel. You and your bank, neither you nor your bank owns all the routers and all the internet connections between the two of you. You might not even own the Wi-Fi that you're connecting to do that. So how do we do that? Well, there are many ways to do it. Encryption is the most clearly obvious method for secure communications over an insecure channel. But you and your bank have to agree on an encryption key, and you have to do this over the same insecure channel. You typically would use some type of secret sharing method to do that, and ideally, you'd both have a shared secret before you get started on this path. So you need to authenticate to the bank, and the bank needs to confirm that it's your bank. The most obvious way for you to authenticate is for you to prove to each other that you both know a password. Okay? And that's one way to do it. One method is for both you and your bank to generate a challenge. Let's say you generate a 16-byte challenge string. It may not seem like a lot, but realize it's 128 bits. You generate a challenge and you send these to each other. Now, each of you uses the stored credentials to perform some cryptographic operation on both the challenges, and then you send each other the result, exchange the results. Now, because you know the challenges, right? You know the one you sent to the bank, and you know the one the bank sent to you. The bank knows the one you sent to it, and it knows the one it sent to you. And you both know the piece of shared secret. You're able to check each other's work, and you should get the same results. Because the challenge is random, and eavesdropper does not really gain much information, assuming we use very secure cryptographic methods. And since the challenge comes from both sides, it's difficult to spoof either side of the communications, right? A person in the middle attack is still possible. So we might want to use some kind of a layer like some host verification, typically based on certificates that allow us to authenticate that the bank is really the bank. All right, so that's one way to do it. And this is a pretty common way to do things. You've got a client, and you've got a server, and we need to authenticate. A Windows domain controller's NetLogon remote protocol provides an RPC system, remote procedure call system, for remote computers, the client there in that picture, to log on to domain controllers using a challenge response system like this. The shared secret here is the client's hashed account password, and that's known both to the client and the server, that the hashed password is. Great. Let's see how that might unfold. The client and server exchange 8-byte challenges. Both use both challenges and the shared secret to compute a session key. Now, if they both know the password, then they'll derive the same session key from this, and the session key will be used to communicate knowledge of credentials and to authenticate. Life is great. So if we follow this picture, client challenge, server challenge, now we derive the session key, and then the client does some stuff with its credentials, and the server does some stuff, and we have this signed and sealed with the session key, and we're able to go on. Great. So let's think about how we would compute our response. What we do here is, so over here, this string, doesn't have to be 1, 2, 3, it just is in this case. This little string, okay, is what we want to communicate, but we need to make sure it's not going to be seen in the clear. So we append to it this thing, and this in front of it, which we call an initialization vector. And the initialization vector, in this case consisting of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 bytes. We take this initialization vector and we prepend it to the plain text message, and then we apply AES to this 16-byte window. And AES doesn't do anything by itself. We use the knowledge of the session key and apply this, and we arrive at some encrypted string here, and you'll notice most of this is blacked out. That's because we really only care about the first byte. So we do this, we save that first byte, we take it, we exclusive OR these two together, right? E2 exclusive OR with 0, 1 is E3, and we replace that one. We slide that 16-byte window over 1, and we repeat the process. We get a new byte, we exclusive OR with this one, and we keep going until we wind up with a heavily encrypted message, right? Our clear text was 1, 2, 3, 4, 5, 6, 7, 8. Our encrypted is E3, 98, F5, so on, right? It's this complicated, nasty looking message. Then we can throw away the initialization vector and transmit this, and life will be good. Well, it turns out that Microsoft uses all zeros for the initialization vector. Now, that's not bad in itself. It may seem like that's a bad thing. It's not random, but we're still going to apply AES to it and generate some string of nonsense down here, even though this is all zeros. Yeah, but we really don't care about the whole string of nonsense. We really just care about the first byte of that string. That can still be anything. There's 256 different possibilities for what that first byte might be. But one of those is the possibility that it might be 0, which means I would exclusive OR my clear text with 0, making no change to it, and resulting in the same clear text being down here. And then I would apply to this all string of zeros, right, still all zeros, AES, resulting in a 0, and putting it here. And as long as these are all zeros and these are all zeros, I keep walking across and doing that, provided I've chosen a session key that yields a 0 in this position. I just need a session key that gives me that. But you know, the session key is going to be this random thing. Well, ideally it's cryptographically strong, which means it's high in entropy, which means that I have a lot of uncertainty about what that first byte's going to end up being, and it should end up being 0 about 1 in 256 trials. So I just keep trying. I request a session key, I check to see if there's a 0. If there's not, I request another session key, and I keep going until I get one that gives me a 0, and then I'm off to the races. I just immediately do the work, and out comes an all 0 ciphertext. That's great, because now I know the ciphertext. But won't the server lock us out after a few trials? Here's the trick. We never let the process get that far. Okay? If we don't get a key we like, we don't proceed to try authentication. Since we never tried to authenticate, it doesn't lock us out. Right? We just keep doing the challenge until we get one that we like and we're done. Keep in mind, we don't actually know the session key. But it turns out we can disable signing and sealing by requesting that the server disable signing and sealing. And then we're off to the races, okay? And we can do things like, once we're on the domain controller, we can set the password to, let's say, an empty password, and then we're good for a long time to come. This is not a great set of circumstances to be in, and in fact, it is, of course, another nasty vulnerability. In this case, there it is. It was discovered in 2020 in the glorious year of COVID, and it's called Zerologin. So how did this happen? Well, there was an assumption about the security of the crypto system, and that assumption is that the initialization vector is random. That is an assumption built into the strength of the crypto system. We need an initialization vector. We could use one that's all zeros, but that would violate this assumption. So we violated the assumption, and it's bad. By the way, this gets a nice score of a perfect 10. Weaknesses occur when assumptions are not enforced. Talked about this before, right? Interfaces, when you don't account for the whole domain, and when assumptions are not enforced. And here we have an assumption that was not enforced. If you're using a secure component, make sure you honor the security assumptions that actually are needed for that component to function correctly. All right, there was homework, and the homework was to steal a car. There you go. Your mission is to build an attack graph for stealing a car. Oh, wait, that's right. Build an attack graph. Don't actually steal the car, please. Don't steal the car. Build the attack graph for stealing the car. Hopefully you've been doing that. I've seen some of you have turned that in already. Here's your attack surface and some information about it. And then here's some other information. I think you've all got this. Let's talk about security models. We talked about two previously, the Bell-LaPadula and the Biba model. Let's go ahead and talk about security models a little more. There are others. There are lots of others. We're going to talk about one more, and I think we'll be done with security models. So remember the Biba model. The Biba model can feel wrong because you read up. That's the thing that seems to perturb most people, is this line right here. Right? If I'm at this level, I can read stuff at this higher level, and that seems to feel strange to me. But it really enforces the notion of data integrity. That's the key behind the Biba model. And so we might ask ourselves, is there a different way to think about the problem? Maybe instead of integrity levels, maybe we can break things up and try to treat them individually so that it will make more sense to us. Really, we're just going to move the problem around, of course, but with the right set of assumptions, maybe we can get somewhere. So here we go. We're going to think about the world in terms of change management, determining when and how changes to objects can be done by subjects. And of course, we're going to limit the interaction between subjects and objects because that's what security means, right? Okay, so over here is our subject, and we have some objects over here as well. And we arrive at the Clark-Wilson model. So the Clark-Wilson model brings us three principles. No changes to objects by unauthorized subjects. Okay? If you want to change something, you have to be an authorized subject, an authorized person to make that change. No unauthorized changes to objects by authorized subjects. Right? You may be authorized, but the change you're trying to make is something that you're not permitted to do, and that's bad, right? That would be like, what is it, writing down in the Biba model. And we want to maintain both internal and external consistency. So we're really getting at data integrity here, okay? And these are regarded as the three integrity goals or the three rules of data integrity. So we have some words here that are carrying around a lot of meaning. They're doing some work for us. Authorized changes, internal and external consistency. And those are really doing a lot of work for us. Enforcement. Well, subjects will not have direct access to objects. You can't reach out and grab object A and do something with it. You can only access these objects through established, well-known, validated transactions, and we call those transaction procedures, or TPs, transaction procedures. We have a set of separated activities, each of which can be implemented and then proven to be correct and secure. So just writing some code is not good enough. You have to write the code and also prove that it's correct and prove that running the code preserves all the security properties that you want. Now, someone's got to write the code, clearly, and someone has to prove the code is correct. And Clark-Wilson says those have to be different people. That's a separation of duties. So you're going to do your work, and this other person is going to check your work. So it's sort of a two-person rule there. Enforcement, well, this is probably too onerous for everything. There's lots of things where maybe this is too much. And there could be a couple different reasons. Maybe there's some data that we don't care about. It's not really meant to be secure data, so we don't need to go through this process for it. And maybe these transactions need themselves to have access to data, and that would be, probably some other data. So we also need to have unconstrained data items in addition to our constrained data items. Constrained data items can only be accessed by these transaction procedures, but unconstrained data items can be accessed directly. Great. So access to the constrained data items is through the transaction procedures, and they've been proven to show that they maintain all the security properties. Great. Does it guarantee integrity? Well, we're getting there. We now talk about things in terms of triples, right? We have a subject here, we have a transaction procedure here, and we have an object over here. And that triple tells us who's doing the action, what they're doing, and what they're doing it to. And these triples are key to a lot of the Clark-Wilson stuff. So we can apply a transaction procedure to one or more CDIs, and that might yield a new CDI, right? I might take object A and object B and tell the system merge those two, and that produces a new constrained data item, and it has to be written so that it's a container for the right data, and it has the right properties, and everything's been proven so that that works. Or I might take object A and generate a new object C, let's say, from it. Okay, and that has to be proven, etc. But what about unconstrained data items, right? These could come from anywhere. They're unconstrained, right? If I can directly write them, and if a procedure might use them, I might be able to slip something in here that breaks the security model. So maybe at some point we need to, if these are going to creep their way, if information from these unconstrained data items is going to creep up into the constrained data items, we need to give that some thought. And so applying a transaction procedure to an unconstrained data item could violate the assumptions. So what we'll instead do is we will create special transactions that can take an unconstrained data item and produce a constrained data item from it. So we take this in, we make some guarantees about it, and then yield one of these. And that way we can get new data in, and we can work with the unconstrained data items as we need to. Also, we have to have a way to verify the overall integrity of the collection of the constrained data items. And we use an integrity verification procedure to do that. So it will run and it will verify that all of our constrained data items are in a consistent and valid state. What's a valid state? Right? We keep adding new words and we have to chase the definition of those words. The integrity verification procedure checks our constraints on the CDIs to make sure they're valid. And what might that look like? Okay, well, let's take a concrete example. Suppose we know yesterday's ending balance for our bank account, and we'll call that EB, ending balance. We know the deposits over the current day are D, and we know the withdrawals over the current day are W. The current balance that we get is, let's say, current balance CB. An integrity constraint would be ending balance plus deposits minus withdrawals has to be the same as the current balance. So we can actually check that. We can run through the ledger and make sure that that's all correct. And if it is, great. That's one check, and there could be many, many others. But how do subjects and objects get authorized, right? We need a way to make that happen, and we introduce a new model, which is the take-grant model. An administrator can grant a subject some rights, and here's a collection of rights that you have. The subject can then take rights, and it can potentially, in some cases, grant additional rights to other subjects, right? So now you can grant rights to someone else, and you can revoke rights to that person. And at the top, there's someone who can do that for everybody. So you have administrators that can do that for everybody. They can then dole them out, and then you can act locally to manage the rights, etc. And so that's how things get authorized. The Clark-Wilson model has a lot of moving pieces. If you go through the paper, which is in the bibliography, there's just a lot there. And I wanted to find a nice succinct statement of it. And I found one. It turned out Wikipedia had one, and I stole it, and it's on this slide. Because there's just a lot going on in the Clark-Wilson model. There's just a lot of stuff about separation of duty and when you use transaction procedures and how UDIs become CDIs, etc. That's just a lot of stuff in there. There are certification rules. Those are the C's in this row, and there are E's, and those are enforcement rules, right? A certification rule would be when the integrity verification procedure is executed, it must ensure all the CDIs, the certified data items, are valid. An enforcement rule would be system must maintain a list of certified relations and ensure only trusted procedures are certified to run on CDIs and change that CDI. So there you go. A lot to think about there. We're not going to get much deeper into this. We've really hit the highlights of the model, and I think you see what's going on. So the question is, security achieved? Right? Have we done it? Have we solved the problem? So we can expand this. Can we expand it to address confidentiality? Because, believe it or not, we never addressed confidentiality. We only talked about maintaining integrity of the data, right? Like the Beaver model. So there's been a lot of work on this. A lot of people have done various stuff with it. But at the end of the day, the Clark-Wilson model turns out to have a problem. And the problem is verification. Verification features very prominently in this model. I have to verify that these trusted procedures work correctly and that they preserve all the right properties, and I have to have a set of integrity verification rules that I can prove show me my data integrity is maintained. Verification of software is hard. Okay, it is. And proofs of correctness for software components can be invalidated if I can show that your initial assumptions didn't hold. For example, I find a bug in the compiler, and now all that work can potentially be thrown out. Or I find a bug in the processor, or if someone finds Rowhammer, right? There are lots of things that can invalidate that work. So it's a huge amount of work to prove these things correct. And they stand on top of this set of assumptions that we don't have any super high degree of confidence in. So there is, in fact, a Clark-Wilson light model that forgoes the formal verification in favor of things like very rigorous testing, and that can be good. But again, you can see what's happening. We're starting to have to back off some of the guarantees to make the system more practical. All right, let's talk about the midterm. And that's it.